next we have example 1-3, which is about a geometric statement that you already know from Euclidean geometry. It's about the centroid of a triangle. And the claim is just this: show that the three medians of any triangle meet at a common point known as the centroid of the triangle, which divides each one of them in the ratio 2:1. Now, in spite of our familiarity with this statement, let us still see it in this figure. So here you see the triangle ABC, and these are the midpoints of the sides. D is the midpoint of the side BC, E is the midpoint of AC, and F is the midpoint of AB. And we have also joined these midpoints to the opposite vertices and obtain these line segments, which are actually the medians of the triangle. The claim is that they all pass through a common point which we have called G, and that point divides each median in the ratio 2:1. Exactly in what sense? Exactly in this sense that as you start looking at this median starting from A and then you consider D, the ratio is 2:1. It means that AG is to GD. These two lengths are in the ratio 2:1. AG is twice the length of GD. This is what we have to prove. Now we are going to do it using vector algebra. You may already have come across the proof of this fact, which is a purely geometric proof which uses properties of similar triangle. In school actually, we all did. But we would see that using vector algebra we get a very slick and short proof. And we write it as this solution, where we have redrawn the triangle ABC, and this time we are not drawing all the medians. We have drawn only one median, AP. This time we are calling the midpoint of the side BC P, and we have joined P with A to get this median AP. And also you may note that there is a point lying somewhere outside or inside, it does not matter. I mean this point O, and we are going to consider this O as our origin, and we will consider position vectors of these points A, B, C, P with respect to this O. You can already see three position vectors OB, OA and OC, which are respectively the position vectors of B, A and C relative to O. That's what we are next going to write. And then we will see how we can use these position vectors. So we write like this: let the position vectors of these points A, B and C, these vertices, relative to some origin O, be respectively A, B and C. A, B and C. Alright. Then the position vector of the midpoint P of the side BC relative to O would be this. Where is this coming from? This is coming from section formula that we saw in the previous video, because the point P divides the line BC internally in the ratio 1:1. That's because it's the midpoint. That is why its position vector relative to O would be 1 times B plus 1 times C divided by 1 plus 1, which is just this, B plus C divided by 2. So let us again concentrate on this figure. This time I am showing the position vector of P relative to O, this vector. It may seem like this A is this vector, but you already know that this A is this position vector, the position vector of A relative to O. This one is the position vector of P relative to O, in fact that is that P. Now next what we are going to do, next we are going to straight away consider that point on the median AP which divides AP in the ratio 2:1 and find its position vector. We are calling that point X. Now how can we find the position vector of X relative to O? We can using the section formula, because we know the position vector of A, which is our vector A, and the position vector of P, which is this, and the ratio also 2:1 in which X divides AP. So again another use of section formula is needed. So we continue by writing about x. Let x be the point on AP which divides it in the ratio 2:1. Then the position vector of x relative to O is this, which we are naming x, say vector x. Now what do we know about the section formula? What did we learn in the previous video? That you have to multiply one of the vectors. I mean, there are two vectors, right? The position vector of P and the position vector of O. You have to multiply the position vector of P by that number which is far away from it, not the one which is near it. The one that is near it is 1, but the one that is far away from it is 2. So 2 times the position vector of P, that is 2P, plus the same thing for the position vector of A also. You have to multiply this one by the number which is away from it, that is 1. So 1 times A divided by 1 plus 2, the sum of these two numbers which form the ratio. And now we are just going to use this expression here and let's see what comes out. So from this equation we can clearly see that 2P is B plus C and 1 times A is just A. So that's how we get A plus B plus C divided by 3. So that is the position vector of this x relative to O. In terms of what? In terms of the position vectors of A, B and C. That means A, B and C. And here is the next observation. One can verify that the position vectors of similar points on the other medians are also equal to this thing, this vector. For example, if you consider the midpoint of AC and say you call it Q, okay, let me write it here, say this point. You call it Q and then you draw the median joining B and Q and then run the same process with BQ. That is, you consider a point which divides BQ in the ratio 2:1 and you find the position vector of that point, not the position vector of Q, but that point which divides BQ in the ratio 2:1, you would find that it's exactly this. And similarly for the remaining median, the third median. What does that mean? It just means that all these three medians would then have to pass through a single point. Actually, these points that we are talking about, x and you may call that other ones say y, they turn out to have the same position vector relative to a fixed origin. So they have to be the same point. So that is why the three medians pass through the same point, which of course, the way we have constructed these points, that point, these points means they coincide and become one point. That point divides each median in the ratio 2:1 when the median is considered in this sense from vertex to midpoint. So there the claim has been proved. We have another example where we are going to see the bisector theorem, angle bisector. You consider this triangle OAB. In the triangle OAB, the bisector of the angle AOB, that means this angle. This is the angle bisector. It bisects the angle into two equal parts. Bisect means into two equal parts. And that bisector meets the side AB at the point P. This is what we have to then show. AP divided by PB equals OA divided by OB. This is how the author starts the solution. The reason for naming this vertex O might have been already guessed. I mean, we are going to consider this as the origin, and that's exactly what we do. Let O be the origin and let the position vectors of A and B relative to O be A and B respectively. And let us also give simple names to the magnitudes of these vectors. Let us call the magnitude of A just the letter A and the magnitude of B just B. We are going to need this. And then the author says this next. The point with position vector A plus B means this A plus B, does not lie on OP, on the line OP in general, but the point with position vector A hat plus B hat does, where A hat is obtained from A by dividing it by its magnitude. So that means A hat is the unit, and that is why we are using this hat notation. It denotes unit vector. It's the unit vector in the direction of A. It has the same direction as the vector A and it has magnitude 1. And B hat is the unit vector in the direction of B. But why? How is this true? And what's going on here? Let's try to understand. To understand this part, we have drawn these two extra figures which show just this triangle but only from a different perspective, which you get by rotating it like this: OAB, OAB, OAB. But you don't see just triangle, you see parallelogram in both the cases. I will say why we have two cases. Actually, the cases just show this. In this case, OA and OB have different lengths. In this case, they are of the same length. That means this in particular is a rhombus. Alright. Now, what does the author say? The author is saying here that the point with position vector A plus B does not lie on OP in general. Why? What is that point? How do you calculate the sum of two vectors? By using the definition of vector addition. The two vectors here are OA and OB. You need to first of all have the initial point of OB, that means this point, coinciding with the terminal point of OA, that means this point. So what do? You translate OB parallel to itself so that it comes to this position, and that's why we have to draw the parallelogram. And once you do that, what does the definition of vector addition say? It says that the sum is this vector, this one plus this one. This one means just this one. Okay, so this is the point having this vector as its position vector relative to O. This point does not lie on OP. OP is the angle bisector, whereas this point lies on this diagonal. Why does this happen? This happens because these two sides of the parallelogram are not equal, and that is why diagonals are not angle bisectors. Diagonals become angle bisectors only when the parallelogram is a rhombus. So because of this geometric fact, we have this. However, but the point with position vector A hat plus B hat does. That means it lies on OP. OP means extended OP, and that point is this. So here you can see that it is lying on OP because here the diagonal is itself angle bisector. However, what is going on here? I mean, why does this work? This works because these two vectors have the same direction as A and B have respectively because of this fact. And additionally, they have the same magnitude, and that magnitude is 1 because they are unit vector. So in this case, the two sides have the same length. That is why. And this fact next gives us this. So the position vector of a general point x on OP is some scalar times A hat plus B hat, because we have just now seen that the point, what point we don't really know, but some point which has this as its position vector, A hat plus B hat lies on OP, so it's here somewhere. Now you think of any other point, or maybe this point also, and think of its position vector. So that vector will be this vector, whereas this one is this vector. So obviously that one will be some scalar times this vector. They are parallel and pointing in the same direction. Even if that point lies there on that side, still it will be a scalar multiple of this, The only thing is that lambda will be negative. Because they are parallel, whether pointing in the same direction or in the opposite direction, that does not matter. It will be of this form. And we are giving it some general name also, x vector. And then you write what a hat and b hat are. And then after a simple vector algebra, this is what you are getting. B times vector a plus a times vector b divided by ab divided by lambda. So do you see why we needed to separately write these names, simple a and b, so that we do not have to keep on writing the cumbersome bar notation. Bar means vertical bar notation to denote magnitude, that is why. And next we consider this. Now x will lie on the line AB if its position vector is this. X being any point on OP. OP means the entire line OP, okay, not just this much, not the line segment, but the entire line OP. What if that point also has to lie on AB? That means we want X to coincide with P. What is the condition for that? If that has to happen, then the position vector of X should be equal to the position vector of P. But we already know how to calculate the position vector of P using the section formula. The alpha and beta that you see here are just the lengths of these line segments. By alpha I mean PB and by beta I mean AP. Okay, I did not again write that thing. So the position vector of P relative to O in terms of these things, A, B, alpha, beta is this by the section formula. Alpha times A plus beta times B divided by alpha plus beta. But X already has its own position vector, which is this. So that means if we want X to coincide with P, these two vectors should be equal. Actually, the author has given this a name also, capital K. I don't see the reason for doing this part of the calculation. We can just simply equate this one, and that's what we are going to do, and let's see what we get. So next we write this. So X coincides with P if and only if this vector equals this vector. But each one of them is a linear combination of A and B. And A and B are linearly independent. That is why for these two vectors to be equal, the corresponding coefficients have to be equal. If you do not exactly understand what this part means, what linear independence has to do with these coefficients being equal, please ask in the comment section below. I have kept the comment section, I have deactivated it because of some trolls. Okay, I will open it for this video and for the subsequent videos. So you can write and ask me why this happens. Why does the fact that the linear independence of A and B imply that for this vector to be equal to this vector, the corresponding coefficients have to be equal? Okay, if you do not understand, please ask me. But because of that fact, what is the coefficient of A here? If you forget about this one, okay, you look at this, lambda divided by A. That should be equal to the coefficient of A in this vector, which is alpha divided by alpha plus B. Similarly, lambda divided by B should be equal to beta divided by alpha plus beta. Alpha plus beta, actually, I think I said alpha plus B. So we now stand here finally. But are we really near what we want to show? That is, this divided by this equals this divided by this. We are almost there. Because you see that we have the length of this vector here, A. We also have B. And we also have these lengths, beta and alpha. So what do we get from these two equations? From these two equations, we see that there is a common thing. Of course, there are many common things, but we see this lambda, which we don't need. Okay, we need to get rid of this lambda. So what we do, we note from the first equation that lambda equals A alpha divided by alpha plus beta. And from the second equation, we also see that lambda simultaneously equals b beta divided by alpha plus beta. So that means these two numbers are equal. And then you cancel alpha plus beta from the denominator on both sides and you do cross multiplication. So that's how you get a divided by b equal to beta divided by alpha. A divided by b equal to beta divided by alpha. You go back and see that this is what you wanted to prove.